If you looked at the schedule, you noted that we have another test on Monday. Seems like they're coming a little too quick here. This test is going to be a little more reviewish over what we've studied so far, because we're getting ready to kick off our real problem, and that's the hydrogen atom. So we're going to have a test that's not just over chapter 3, but over chapters 1 through 3 with more small in the small problems. Not as big as the small problem in the last one.
Gotcha.
And so you'll want to, and I have at the end of this, we may not get to my review slides, but I have some review slides just to help, clarify that. In case I don't get there, any questions about the exam?
We're studying the first 2 exams.
Mm-hmm.
I guess what I should say is how much of the stuff off that wasn't inside the first 2 exams will be on the 3rd exam, other than chapter 3 of it.
I don't have a percentage, but I will be looking at problems that gave you trouble. So for instance, commutators. There's going to be commutators on this next exam because
that's fine. We make all the content commutators. We know what's wrong, man.
Yeah, I mean, because it's making sure that we're up to date and ready to move forward.
Yeah.
So in that regard, I will look back. I clearly won't ask the same question.
Yeah, of course.
But I will look for themes that were missed to make sure that those have been shored up. Okay, so this says review, but really I want to continue where we left off last class period. So we were working on finding the eigenfunctions and the eigenvectors to this operator A. And we had done that. So we had eigenvalue 1 was 3, and then the eigenvector 1 was 0, 0, 1. Eigenvalue 2 was 2, and the eigenvector that was associated with 2 was 1 over square root 2. That's our normalization constant, 1, 1, 0. And finally, eigenvalue 3 minus 2 is the eigenvalue, and then the eigenvector 1 over root 2, 1 minus 1 and 0. That's all fine and dandy, but you know what we like to do? We like to have our operator such that that the eigenstates are the states of the operator in a simple fashion. These eigenstates, well, this one's simple, but these two aren't simple. They're linear combinations. If we were to define x, y, and z as the 3 directions, then this is a linear combination of x and y and a linear combination of x and y. Using my fingers as an example, here's x, y, and z. And the z-axis, this one here, we agreed on, but it's rotated like that. So what I want to do is say, well, how can I rotate the coordinate system so my eigenvectors are 1, 0, 0, 0, 1, 0, and 0, 0, 1? That would be really useful because that would diagonalize the operator. Sound like a good project? Yeah, okay. Have you done this in your linear algebra class?
I think we've done something similar.
Okay.
I'm not totally sure.
What we're going to do, if you've done something similar, what we're going to do is undoubtedly easier than what you did in your linear algebra class. So it's got that going for it. We do this by creating a similarity matrix that will diagonalize. What is that similarity matrix? Well, here is the definition for the inverse of the similarity matrix. That is, for the inverse, s minus 1 equals, and then you have blah, 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 where it's row column, so I is representing the row, j is representing the column, is equal to aj. That aj means I'm going to take eigenvector 1 for j equals 1, eigenvector 2 for j equals 2, and eigenvector 3 for j equals 3. And so the j was the column. I is the position, the row. And so all I'm going to do is slam together these 3 eigenvalues, or eigenvectors. So it's very simple. My similarity matrix is just going to be A1 is 0, 0, 1. A2, notice the 1 over square root 2, I have to put that in now. 1 over root 2, 1 over root 2, and 0. And then A3, 1 over root 2, minus 1 over root 2, and 0. That's not hard to make. All that requires is that you just take your column vectors and you slam them together to make a square matrix. But of course, that's the inverse of our similarity matrix. We need to find both the similarity matrix and its inverse because the transformation is going to be A operator prime is equal to S minus A operator, or S minus 1, excuse me, S. So I need to find what S is as well. And that's where life gets amazingly easy compared to what it could be. If we have an orthonormal set of bases, which we do for a quantum mechanics system, then the similarity matrix is the Hermitian conjugate. Okay, I have it right. The inverse of the similarity matrix is the Hermitian conjugate. So all I have to do is take the Hermitian conjugate of S minus 1 to get S. So that's what it's supposed to be a dagger, but I don't have dagger in my character set, so that's why it's a plus sign. So my similarity matrix is just the Hermitian transform, which means, or Hermitian conjugate, which means you transform it, you reflect it about this axis, and you take the complex conjugate. Now, in this case, my matrix was all real, so the complex conjugate part doesn't show. But you do have to remember you're taking the complex conjugate as well. So I just reflected on that. So I have this one moved from there to there. Those moved across. And there's my similarity matrix. Very quick process. What do I do with that? Well, I just showed the transformation, except for apparently I showed it backward. I put S minus A S, S minus 1 AS. Let's go to the book and make sure which one was wrong, me now or me when I was making this. And if you look at, for instance, equation 8.64 on page 447, you see that what I wrote last night is the correct form. So let's just go up here and fix it. Where did I write that? There. It's all fixed. No one will know any better unless they watch the video. So now we just transformed that matrix. So I have my A prime is equal to SAS. I put minus 1 here because it's the inverse. By the way, you remember the inverse matrix, you multiply them together, you get the unit matrix. And so you just go through the math. You guys are good at multiplying matrices by now, right?
Yes.
Okay. Wait, you said yes and no?
I said we hope.
Oh, we hope. Okay, good. So multiplying that through, you get this for your new operator. Some things that are preserved in the transformation. The trace is preserved. The trace being the sum of the diagonal components. So 3 plus 2 plus minus 2 equals 3 is the trace of my transformed operator. The trace of my original operator was 0 plus 0 plus 3. That trace did not change. So that's a good way, one way of testing to see, did I do it right? There's a second thing that doesn't change. I think that's the determinant of the matrix doesn't change. The determinant of the matrix, I didn't focus on that one as I was preparing, so I don't want to go too deep on this because I could be wrong on that. But the trace doesn't change. That's actually an important way of identifying your matrix. So now we have transformed our matrix. We can immediately say, well, the eigenstates that work with this are going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right, because if you have A prime, let's use F again, then that's going to give you the equations of and if you multiply those, you'd have, excuse me? Oh, yes. Yes, you're right. You're right. If you multiply those, you would have 3a equals lambda a, 2b equals lambda b, and minus 2c equals lambda c. And if lambda is equal to 3, only the top one could be correct. If lambda is equal to 2, only the middle one can be correct. If lambda is equal to minus 2, only the bottom one could be correct. So that means you have the three cases are those are what you get for the three cases. You have to set two of them equal to 0 because you're never going to have 2b equals 3b. You're never going to have 2b equals minus 2b. And so that's where you get these from. So you can see, oh, yes, that did that diagonalizing made it so I'm going to have the simple 1, 0, 0, 0, 1, 0, and 0, 0, 1. But we're going to do one more check, transforming our eigenvectors. So we transform the eigenvectors in similar fashion. The new eigenvector is going to be that S, the similarity matrix, multiplied by the old eigenvector. And so I did it with A1, A2, and A3. And so here's the similarity matrix. Here's A1. You multiply 0 times 0, 0 times 0, 1 times 1, 1. Yay. 1 over root 2 times 0, 1 over root 2 times 0, 0 times 1, 0. You see how it works. And so sure enough, that similarity matrix transformed my eigenvectors so that now I have the simple diagonalized matrix and eigenstates. All fine and good? Okay, let's do it again. Starting with B now. So the first thing we had to do was, and this is actually useful things for the test, just so you realize. One, okay, I want a thicker pen now for some reason. Find the eigenvalues. 2, find the eigenstates. 3, find similarity matrix. Okay, so there's the steps we're going to do. 1, find the eigenvalues. 2, find the eigenstates. 3, find the similarity matrix. 4, diagonalize the operator. 5, transform the eigenstates. So let's start. How do I find the eigenvalues?
Well, we use the the characteristic equation is what's called, but was it operator times uh,
That's what you're talking about?
yeah, that's the characteristic
Yeah.
Equation. Yeah.
And that is only true if it's only true if that's true. So we do the determinant test to find the eigenvalues. So that's going to be now this is a little more difficult for finding the determinant than what I did before. So I will just alternate. Chris, what's the first term in find the matrix here? Or find the determinant of the matrix here?
So if we take the top, say the top row.
Okay.
Our negative lambda times, are we saying lambda mod squared?
No. This is just lambda squared.
Okay, so lambda squared minus 1.
Okay, there's our first term. Indy, what's our second term?
Okay, so now we are going to do minus 1 times negative lambda minus 1.
That's right. Okay, back to Chris.
So we have plus 1 times 1 plus lambda.
All right, there's our equation. You look at this and you're like, oh, goody, right? Isn't that what you're thinking? Well, if you expand it out, that gives us this. And then you look at this and you say, what in the world? How do I do that? Well, there is, let's see, I was thinking about this morning. Actually, it was last night. That was correct, but there's an easier way to write it to get your answers. Here's the easier way to write it. Minus lambda times lambda squared minus 1 is lambda minus 1 times lambda plus 1, right? And then minus, 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 I can just change those to all pluses. And that makes these two the same thing, so it's just going to be 2 times lambda plus 1. Now that I have that like that, I see that I have lambda plus 1 in both terms. So I factor it out. Now it's manageable because minus lambda squared plus lambda plus 2 can be further I have to have one of them is 2, one of them is 1, and the one that's going to be multiplied by the negative has to be the smaller because this middle one's positive. And boom. Now it's easy. So I've done, of course, I did the work already, so that's why I knew that was the way to do it. What are my roots then?
So we have 2 and 2 sets of -1.
Okay, so there's my eigenvalues. As he said, 2 sets. Well, it's 1 set, but 2 occurrences of -1. What do we call it when we have 2 eigenvalues that are the same?
Is it degenerate?
Yes. So this one was a harder problem because it's degenerate. But we've done the first part. First part was find the eigenvalues. We did that. So next, find the eigenstates. So rewrite the matrix so we don't forget it. Here's our matrix. There's our eigenvalues. How do I find the eigenstates?
Right, so do we do like the matrix minus the identity matrix times the different lambdas, and then you can
That works.
so, would that work?
Yeah, we're going to go back to what these equations represent. So the way I do it is slightly different than what you said, but it is mathematically identical. So I put it as that form, right? It's the same equation. And so I'm going to have 0, 1, 1, 1, 0, 1, 1, 1, 0 times ABC equals lambda ABC. How do I know it's ABC? Well, because it's a 3 by 3 matrix, so I have 3 items, and I just chose A, B, and C to be constants. So if I multiply those through, I get 3 equations. What are those 3 equations?
So you get B plus C is equal to lambda A.
And
A plus C is equal to lambda B. A plus B is equal to lambda C.
so I have those 3 equations. And then I have to put in my different lambdas to check them. So we'll have, if lambda is equal to 2, come on. Then I have B plus C is equal to 2A. Excuse me. A plus C is equal to 2B. And A plus B equals 2C. What do I do with that?
We have 3 equations, 3 unknowns.
Yeah.
We try solving them.
Well, yeah, we definitely want to solve this. So let's do this. Let's just take the second equation. It's already solved for B, so let's plug it into the first equation. And so we'll have B is equal to A over 2 plus C over 2, right? That's B, plus C is equal to 2A. expanding out or combining terms, subtract the a over 2 from both sides, and you have 3 over 2c equals 3 over 2a, which we more commonly would write as c equals a. Now I'll put c equals a, put that in here, and I'll have b plus a equals 2a.
Right.
So what's b equal to?
A.
So what's my eigenvector?
1, 1, 1.
Okay, 1, 1, 1 would be unnormalized. I can do the normalization in my head at this point because 1 squared plus 1 squared plus 1 squared is 3 squared. And that has to be multiplied by normalization factor equals 1. It turns out that my normalization factor is 1 over root 3. So there's lambda 1. That wasn't hard. Or not lambda 1. Lambda 1 was 2. Yeah. And there's no prime there either. Getting ahead of myself. So B1 eigenvector is 1 over root 3, 1, 1, 1. So now let's go on to lambda 2 equals minus 1. We've already done the equations up there. So we're going to have b plus c equals minus a. A plus c equals minus b. A plus b equals minus c. If you look at those equations, you should notice something a little disturbing.
The addition of the 2 equals a negative number.
They're all the same equation. I can't really solve it if they're all the same equation, can I? So what do I do? Any ideas? I make an arbitrary decision. Let's just choose something that works. It has to be orthogonal to the one we found already. And it has to be normalized. We have those two rules. And then we have the sum has to be 0. So I'm going to go with the easiest thing I can think of. The easiest thing I can think of is a minus a 0. Why did I go with that? Well, I can normalize that real quick. Right, it's easy to normalize. And I can check the orthogonality. B1 has a constant of 1 over square root 3. B2 has a constant of 1 over square root 2. So I put the two constants out front. Screwed up there, didn't I? That's a 1. If you multiply these, I have 1 times 1 is 1. Plus 1 times minus 1 is minus 1. Plus 1 times 0 is 0. It's orthogonal. right? It was pretty easy to see that it was going to be orthogonal. If I had not been able to see that, I would have said, well, let's just try. Let's set one of them equal to 0. One is A, one's minus A, or one's A, one's B. Well, it had to be A minus A because they have to add up to 0. Right, so I just, go ahead.
How do we normalize it?
Okay, how do we normalize? Sorry, I should have shown you that. That's the rule for normalization. The inner product, as we say, is 1. And so for B1, before we normalized, they were all the same. So I had, wrong thing, that's right. So I had A equals 1. And so when you multiply that out, that's A squared plus A squared plus A squared. So 3A squared equals 1. And so then A had to be the square root of 1 over 3. So, I mean, that's a good question. I'm sorry I didn't go through that.
No, I couldn't remember what we had to do for normalization. Yeah, we remember you told us last time, but we just.
Yeah, it's okay. No. There's no problem with that. So let's go through the normalizing of B2. So remember, I just kind of made this up as I think this will be orthogonal. If it hadn't been orthogonal, I would have come back and said, okay, what'd I do wrong? But I had only 2 rules. It has to be orthogonal and the sum of the elements had to be 0. So I just chose A minus A 0, A minus A 0. And so that's how I got to 1 over square root 2. So I normalized it, but then I also had to check to make sure I had chosen something orthogonal, because I just came up with that out of the thin air. Right? There was nothing really magical about how it came up. I came out with the thin blue air, whatever.
So in a situation where we had our 3 equations were all equal, would we just use, in every case, A negative A 0 as just the easiest thing we can use? Or is that something that only would work with this?
Well, the 3 equations all being equal was not the actual key to it. The 3 equations all being equal was the key that I've got to make crap up.
Yeah, right.
But that the equations were A plus B plus C equals 0 is why I had to have it. So I had 1 minus 1 and 0. Or I could have had, like what I was looking at this last night, I found someone online that actually solved this problem, and they chose 1, 1 minus 2. 1, 1 minus 2 follows the same.
Okay.
Right, so I just made it up thinking this should be orthogonal to 1, 1, 1. And if you can't think what must be orthogonal, well, then you just leave them as, A, B, C, and you do let's just do it that way. If you didn't, this is actually what I did at first last night before I started thinking clearly. So I said, let's just set B2 equals ABC. Well, wrong. That's so B1, B2 well, we had our rule that A plus B plus C had to be 0. So it didn't matter, it turns out. I could choose any A, B, and C. As long as A plus B plus C adds up to 0, it's going to be orthogonal. So I could have chosen all kinds of random things as long as that's true.
Okay.
Okay, so now we found A and B, or B1 and B2. What are we going to do for B3?
Make up something else.
We're going to have to make up something else, that's right. But that something else is more constrained because it has to be orthogonal to both B1 and B2. So now I can say B3 is equal to ABC. And then, of course, my B3 with B, what did I just do? This here. Nope, not that. Wow. I'm really organized. Yeah, this one here. My B3, B1, B3 is going to look exactly the same, right? But my B1, B2 is not. So I'm going to have, or B, let's do B2, B3. And if they're orthogonal, what is this going to have to be? So now we multiply it through 1 over root 2. Obviously, the 1 over root 2 doesn't matter if it's going to be 0. So I have A minus B equals 0. So A has to equal B. And if you don't remember what we've done, you might feel like we're stuck. But what we've done is we already had the equation A plus B plus C equals 0. So that means I'm going to have A plus C equals 0. C equals minus 2A. So now I have a vector and now I have to normalize it, and I'm done. So I saved myself writing the row and column here. So what's my normalization constant? So now we have B3 is equal to 1 over square root of 6. 1, 1, minus, yeah, 1, 1, and minus 2. So we have now we found the 3 eigenvalues and found 3 eigenvectors. Eigenvectors 2 and 3 are not fixed in stone. I started with me making a random choice and then going from there, right? Because this is a case where, using my 3D thing, I could have rotated about one axis and it wouldn't have mattered. So to summarize what we have now, we have for B equals 0, 1, 1, 1, 0, 1, 1, 1, 0. We have lambda 1 is equal to 2. So there's what we found so far. We found the eigenvalues and the eigenvectors. What was the next step that I wanted to do? Okay, so similarity matrix. So what's the inverse of the similarity matrix going to be? Go ahead.
For lambda 3, is it 2 or is it negative?
Oh, minus, yes. That's reasonably vital. It's not the right answer without it, in other words. So what's the inverse of my similarity matrix?
Just smash them all together, all the vectors.
Okay, and then we have to transform that. Now we have to actually do our math. For reasons that we'll call lack of sleep, I have to go and check once again to make sure that I do my transformation in the right order. I know it's ridiculous to not remember that. Whoops. Can't read. I know you can't do this, but I'm lazy. Okay, maybe I'm also not smart. You guys busy multiplying matrices?
Yep.
Hooray. Do we all get the same place?
I got the 2.
Well, we only have a minute and a half left, and this is just, it's math. So let's.
I got a 2, a -1, and a negative, but I did not get those numbers.
Well, did you have the middle set the same as I did?
I got the middle one. I got the -1, but then I had.
No, by middle I mean this row here. Specifically this matrix, was that the same? Or did you do it a different way?
No, I got the exact same thing.
So then if you multiply this minus.
Yeah, I just multiplied.
Minus and minus. And of course it's 1/6, 1/6, and 4/6.
Oh, wait, I know what it is. I took the, for some reason, I somehow dropped the square roots.
Oh.
So I had 6
over 36.
6 over 9 rather than 6 over the square root of 9.
9?
Yeah, because if you take the square root of 3 times square root of 3, right? It's something completely different.
Oh, okay. You're not talking about this one then.
No, I'm talking about, so like for instance for the first one,
yeah.
When you go to multiply those across, and you multiply them across and you
yeah. So you had 2, 4, 6 over 9. Yeah, I see.
Yeah.
Okay. We're out of time, so we won't worry about converting the eigenvectors here. Very quickly, let's just look at these slides because we all got to run. This is what we started out the semester with, the origins of quantum mechanics. So now on this one, I'm not going to be as interested in, why was Schrodinger interested in this to begin with? But I will be interested in things like, there's the 2 methods, waves or matrices, and operators and observables, how those interact, because we've seen them both in a calculus version and a matrix version now with this chapter. And of course, the probabilistic idea is that what it means to be an expectation value, what psi means. So yeah, there's the statistics. The wave method by Schrodinger, you have the Schrodinger equation, which now we've learned is just finding the eigenstates for an operator. In this case, the operator is the Hamiltonian, right? So we can now come back and take what we just learned in chapter 3 and say, yes, the Schrodinger equation was just saying that Hamiltonian operator acting on psi is equal to the energy eigenvalue times psi. That's all it is. And so then we find our stationary states and energy eigenstates. And then, of course, the idea of the scattering states. And it was interesting, that question that I had the mistake on the test. One of you did it for scattering states, and one of you did it for state, not, it was fine. I didn't count against either of you for, not interpreting the way I intended it to be, since I wrote it wrong. Combine the time solution, the time independent solution. You had to do that in the last step of that problem. And this here, you better know cold. Wave functions must be normalized and mutually orthogonal. And then the matrix method was devised by Heisenberg. He was just focused on what are my observables. Basically, he's making a matrix that has, the observable values and going from there. And so we've seen now how we can find the eigenstates from that matrix and find the eigenvalues. We had our wave functions have to live in Hilbert space. That means that you have to have them normalizable, and you have to have a complete set, so any vector can be described as a superposition of your eigenstates. And that's completeness, that second part. Your operators have to be Hermitian for the matrices, and the wave function, make sure you know your drag notation. The inner product, that's what we mean by an inner product. So make sure you're clear on that. And if it's in a Hilbert space, that is going to be a finite value, not an infinite value. So the scattering states aren't in Hilbert space. Uncertainty relationships, and then this is the last one. I'm going to focus a little bit more on smaller problems and looking at the knowledge in those small problems. So I'm not going to raise the value of the knowledge part, but there will be more knowledge things in the small problems. Okay, so exam on Monday, and I'll see you again on Wednesday. And you saw that I did upload your exams and grades, right?
Yeah.
And if you have questions, if you think I graded it wrong, please contact me.
Okay. A question for the commutators. Were the commutators wrong or just done incorrectly?
Both. You really can't evaluate a commutator without having that wave function, right? So you don't have enough terms. When you're doing the PX, you don't have enough terms in your work if you don't have the psi with it. You're missing one of the terms, and yeah. So I really couldn't grade it because.
Yeah, that's fine. It makes sense.
All right. Happy Sabbath.